Hi, I'm Scott Knockleby. In this video, we're going to look at some additional examples of assigning modified D&H parameters to robot manipulators. So by the end of this video, you should be able to assign modified D&H parameters to robot manipulators. In this example, we're going to look at the Unimation Puma 560 6-axis industrial manipulator. This was one of the first sort of commercially available industrial robot arms. It has a layout of R, perpendicular R, parallel R, perpendicular R, perpendicular R, and perpendicular R, with again the last three joints intersecting to form a spherical group. So it has a spherical wrist. All right, and this is exactly similar to the layout of the rice that we saw in the previous video, but with one slight difference. There are two small offsets in this robot, which would be a little hard to see in this picture here, but these two offsets don't exist in the rice. In the rice, they would be 0, but in this robot, they have a value. So I'm going to draw the 0 displacement and show you where these two offsets are. So the 0 displacement for the Puma would look something like this. There's Z0 and Z1 here. X0 and X1 here. We're going to draw Z2 into the page. Again, we have some freedom. We could draw it out, but in here we're going to draw it in. This will be Z3 here, X2's here. And this is the offset that the rice has. We'll label it A. All right. But one of the first offsets that this robot has is there's a length B here. There's X3 there. So we have this B, which was 0 in the rice, but it's a value here. As well as there's a length C here. Okay, and that takes us to Z4. All right, with X4 here, and so this is our length D. All right, so the rice had A and D, but it doesn't have B and C. Now these two are exaggerated. They're actually quite small, but just in order to draw the 0 displacement and be able to label things, I've made them a lot bigger than they are. All right, but in reality, these are two small values, but like I said, they exist and they change the kinematics. All right, and now to complete the rest of this the 0 displacement diagram, we have Z5 as part of our wrist. All right, and since the wrists, they all intersect, so that means X5 has to be here. We'll have Z6 down here with X6 here. And then we'll have our tool length, which takes us to Z tool. And X tool there. So there's our 0 displacement. And now with that, we can start completing our D&H table. All right. So again, we're going to go from frame 0 to 1, and then once we're at 1, we're going to go to 2, and so on up till the tool frame. So let's start. We're at frame 0, and we want to go to frame 1. All right, there is no distance between Z, so we know that that's 0. There's no angle between Z, so we know that's 0. There's no distance between X's, so that's 0. And then we have our first variable, theta 1. All right. Going from frame 1 to frame 2. All right, Z1 and Z2 intersect, so we know that this is 0. Z2 is into the page, Z1's up, so that is a negative 90 degree or negative pi over 2 rotation. All right, but x2 and x1 are collinear here, and then we have theta 2. All right, now to go from 2 to 3, you can see we have a number of things going on. Although joints 2 and 3 are parallel, and we should indicate that in our zero displacement, these two are always parallel. Okay, we do have these additional offsets. All right, so the distance between z's is a. They're parallel, so our alpha is 0. There's a distance between x of b, and then we have theta 3. All right, and then 3 to 4, distance between z's is c. All right, we have another angle between z3 and z4. In this case, it's a negative rotation of 90 degrees. We then have d, the distance between x's, and then we have theta 4. 4 to 5, all right, this is our wrist center, so joints 4, 5, and 6 intersect, so we're not going to have any lengths, so those are going to be 0. We're going to pi over 2, the angle between z4 and z3, sorry, between z4 and z5, sorry. Okay, and then 0, then theta 5, 5 to 6, it's going to be 0, minus pi over 2, 0, theta 6, and then lastly, from our frame 6 to our tool, we're going to have 0, 0, L tool, and 0. Our next example is the SCARA, 4-axis industrial manipulator. So the SCARA manipulators are used for pick and place operations in the plane. So they're 4 degrees of freedom, all right, and they are able to pick up something in the plane and then drop it off in another location. So these are good for high-speed pick and place activities. So the layout of it is R, parallel R, parallel P, parallel R. All right, so there's 3 revolute joints and then a prismatic joint. Okay, and it would look something like this in terms of schematic. We have our first joint. It's parallel to our second joint. It's parallel to our prismatic joint. And then we have our final rotation. So in terms of joint axes, we have Z0 and Z1. We have Z2. And here we'll have Z3, Z4, and Z tool. We're going to have lengths A, B, D3 associated with the prismatic joint, and then the length of our tool. So that's a schematic of it, and with that schematic, we can draw our zero displacement diagram. All right, so we start with Z0. Z1 will be collinear. So we have X0 and X1 here. All right, we have a distance A here. Brings us to Z2, which is parallel to Z1. X2 will be here. We then have a distance B that brings us to our prismatic joint. We're going to draw it in the axis for Z3 to be in the opposite direction of Z2, all right, but they're parallel. So this will be Z3. We'll have a length D3 that brings us to X3. Okay. Z4 is collinear with Z3. So X4 is there. Then lastly, we'll have our tool. So we'll have Z tool here and X tool here. With that complete, we can create we can fill in our D&H table. All right, distance between Z0 and Z1, well, that's 0. All right, they're collinear. They're in the same direction, so that's 0. There's no distance between X's, so that's 0. And then we have theta 1. From frame 1 to 2 now, we're going to have a distance A between Z axes. They're parallel, so that's 0. There's no distance between X, so that's 0. And then we have theta 2, our second joint. 2 to 3 now, the distance between Z's is B. The angle between Z's is 180 degrees, or pi. All right, and then we have our joint variable D3. And then we have 0 because there's no angle associated with the prismatic joint. And then 3 to 4. All right, they're collinear, so these are 0 and 0. There's no length between X, so that's 0. Then we have theta 4. And then lastly, we'll have 0, 0, L tool, and 0. All right, and in fact, we could actually switch rows, our prismatic joint and our revolute joint, right? It doesn't matter if we translate then rotate. We could have rotated and translate. The kinematics would be the same. Okay, it's just one little note for this layout. So the final example we're going to look at for assigning D&H parameters is the Stanford arm. All right, and so Stanford arm has a R, perpendicular P, prismatic joint, parallel R, perpendicular R. And this is also a spherical group. So a little different. We have a prismatic joint as part of the main arm. Okay. If we were to draw a schematic of it, it would look like this. There's our first joint. It's perpendicular to our second joint. All right, which is perpendicular to a prismatic joint, which is then parallel to joint 4. And then this is our spherical wrist here. And then we have our tool. So if we were to draw frames here, we have Z0 and Z1. We have Z2. We have Z3 and Z4. Z5. Z6 and Z tool. Okay, so as always, we start with the zero displacement diagram. And for this arm, it's basically everything's going to be straight up in zero displacement. So we're going to have x0 here. We're going to have z0 there. All right, z1 is collinear. This will be x1. z2 is coming out. It's perpendicular to z1. But its x-axis is here. We then have our prismatic length, which we should label here. This is D3, okay? And this length here is L tool, so we'll need those. So we're going to have our length D3 here, with Z3 going up. That's going to bring us to X3. Z4 is collinear as Z3, so Z4 is up as well. Z5 is perpendicular, so it's here. There's X5. Z6 is in 90 degrees to Z5, so it's going to be up. There's X6. Then we're going to have the length L tool to our tool frame. And we'll have Z tool. And we'll have X tool. All right, and so there's our zero displacement diagram. And again, we just start at frame 0 and we see what we need to do to frame 1, 1 to 2, 2 to 3, and so on. All right, so let's start at our base frame to go to frame 1. Well, Z0 and Z1 are collinear, so we know that this is 0, this is 0, this is 0, and this will be our first joint, theta 1. All right, we know that joints 1 and 2 intersect, so we know that A is 0. However, joint 2 is perpendicular to joint 1. All right, and that is a positive 90-degree rotation about the x-axis. And then we have 0, theta 2. Okay, between joints 2 and 3, they intersect. So our A is 0. All right, but they are a negative 90 degrees apart from each other. Then we have our joint value D3. And our theta is 0 because it's a prismatic joint. 3 to 4. All right, they're collinear. So we're going to have 0, 0, 0, and theta 4. And then joints 4, 5, and 6 intersect. All right, so we won't have any link lengths there, so that's going to be 0. But we do have a 90 degrees Z4 between Z4 and Z5. Then we have theta 5. 5 to 6, again 0 because it's a spherical wrist that intersects. They're 90 degrees negative direction apart. 0, then theta 6, and then lastly, to get to our tool, it will be 0, 0, L tool, and 0. All right, and so there is our D&H. So we're going to look in the next video how we use our D&H parameters to solve the forward displacement solution, or solve the forward displacement problem for our spatial robot arms.